Good morning, good afternoon, and good evening. My name is Whitney, and welcome to our first session of our Arista Technology webinar series, Designing and Developing EVPN VxLAN Networks. Today's topic is EVPN VxLAN route types and routing models. We are joined by Arista's own Russell Kelly, Technical Marketing Engineer, and Systems Engineer Mitch Vaughn. First up is Russ.
Thanks, Whitney. All right, so everyone can hear me. Well, good morning, good afternoon, good evening, everyone. It's great to be here and introduce this the new Arista technology series. And first up is a very popular topic, designing and deploying EVPN networks. As was sort of covered in the intro and in the abstract, this is a live session. We're doing it live to a virtual live studio audience. So we're taking questions live. Actually, Mitch will be driving most of the presentation today. Alex and I will be answering some of the questions, answering some of them live, but also, answering some of them in the chat. And to that end, let's move in and have a look at, Mitch, we could just move to the next slide. Be remiss if I didn't just cover what the technology series is as an intro. So we put this together. It is a tech session for engineers, by engineers, by us. So it primarily is configuration, verification, validation on the routers themselves, a deep dive into the route types in this case. But we've identified 6 sessions to start off with that we think are critical in understanding when we're deploying and developing, EVPN VxLAN networks. We've got today's session, which are the core route types and the routing models, which I'll cover in a little more detail in the following slides. But session 2 is also ARP and EVPN. We've moved ARP to be control plane driven. So ARP, as always, ARP suppression is a big topic, ARP optimizations. Then sessions 3 and 4 move into dual homing scenarios. One with MLAG, we'll be looking again at the control and data plane scenarios and actually configuration, best practices, and failovers. So, a deep dive into that. That's actually covered in our deployment guide. And then we'll be moving into the active-active ESI multi-homing, again, which will expand on the above case and the above sort of scenarios, but will include the type 1 and type 4 routes for DF elections, aliasing, active-active forwarding, and so on. Session 5 is another big topic that we have lots of conversations with customers on, and really for scaling, I've called it scaling EVPN environments, and here it's stitching together EVPN, VxLAN pods, or even to that end, MPLS environments. So we'll review the industry standards and adoption. We'll look at configuration examples of layer 2 stretching and optimizing flood sets, of layer 3 gateway use cases where one may take an EVPN VxLAN environment, terminate it, and re-advertise those prefix routes as MPLS VPN. And example, like a disaggregated and also integrated solutions. And the final topic we have tagged is EVPN multicast. So again, reviewing the drafts that are out there, the adoption, looking at the different route types, the layer 2 IGMP suppression, the join and leave sync options, and the layer 3 optimized, inter-subnet optimized multicast routing in the overlay, as well as underlay options with ingress and PIM. So we have these 6 topics tagged. We're looking for your feedback. We have 2 others that are up for mention, which is VxLAN troubleshooting, and also deploying and automating deployments of EVPN VxLAN environments with Ansible and CloudVision. So please provide feedback, and as we go through these sessions, and they can be tuned and they can be added to the agenda. Next slide. So I wanted to add just this slide to give an overview of the RFCs that cover the technologies that we'll be looking at. The first one, of course, and the one that's been around for some time, is 7432, which specifies the BGP address family to advertise MAC and IP, so ARP routes, as well as IP prefixes. And it also defines a couple of different route types for the DF election and for the active-active forwarding. Now, its primary function, of course, is to provide layer 2 and layer 3 VPN services. So the single control plane, the single BGP VPN address family is a major bonus for the customers, and they see this as a reason to adopt it. Importantly, though, I think it's looking at the forwarding planes. There are multiple forwarding planes. So the original RFC 7432 was defined for MPLS forwarding planes. So it had the aliasing label, the SI label, etc. There is another RFC, which is actually what we're focusing on today. Of course, we've termed it the data center overlay because essentially it was born out of an IP fabric underlay, although we have customers using this in different different scenarios in the WAN if they have an IP WAN. And this RFC defined MVO tunnel types. In this case, we were looking at VxLAN. Finally, there is another RFC for provider backbone bridging, and we've taken it as a Metro Ethernet focus. And the diagram below really just depicts the control plane from the original RFC spanned across the different data plane encapsulations. Next slide, Mitch. All right, so EVPN in the data center. And again, these are for reference. So I saw the question was asked, we are going to put these up and they are recorded. So you'll be able to review these and figure out the RFCs. But just wanted to make mention for EVPN in the data center, focusing specifically on A365. No change in the route types per se. It's just focused on a VxLAN encapsulation. The goal, of course, is to provide multi-tenancy, layer 2 stretch, and layer 3 segmentation. And the no difference, I think it's important to understand here with the route descriptors, route distinguishers, and route targets. So the route distinguishers to keep VPN routes unique across the domain, and route targets to identify the routes and import them into the specific MAC VRF or a layer IP VRF, layer 3 VRF that's configured. So no change from like the MPLS infrastructures from years gone by. It's been around. It's a concept we should be familiar with. And VxLAN data plane, it's a MAC and IP, or specifically UDP. Its job is to stretch layer 2 across the layer 3 underlay. That's the data plane we'll be using defined in RFC 348. And quick mention on the layer 3 underlay here. We're using a leaf spine topology. Obviously, it's kind of the de facto now for building out not only data center fabrics, but many topologies and many domains these days, to be honest. It's scaled, it's reliable, it's easy to understand. So in this topology, in this, our demonstrations and going through the series, we're focusing on the leaf spine, closed fabric. We are using EVGP as the underlay routing protocol. We're really just following the massively scaled data center RFC there that's mentioned, 7938. But there are other options. So you can run an IGP as an underlay. You're allowed, you can use ISIS and OSPF, and we have customers who are doing that. We even see a progression towards an IPv6 underlay, and one example that some customers are moving towards is using 5549, which is advertising default loopbacks over a V6 underlay. So I just wanted to point out there are other options. In this topology, in this demonstration, we'll be using EVGP as an underlay, and it's very much a spine-leaf fabric. Next slide, please. All right, so the route types that we'll be focusing on here are circled in blue. So we're looking at the MAC and MAC IP route, type 2, and the IMET route, as well as the IP prefix route. That's route type 5. Route types 1 and 4 we covered in session 4. That is the active-active ESI multi-homing. So you'll get a full view of these, once you go through the sessions. And by the way, just a mention of the sessions, we've designed it to sort of step up through critical pieces and critical components in building this. They are recorded, so you can sort of come back and have a look at them. But, once you go through this whole series, you will get a detailed overview of how all of these route types come into play for multi-homing and sort of MAC and IP prefix advertisement. Next slide. The laundry list of multicast route types for EVPN. In our demonstrations or the session, at session 6, we'll be looking at route types 6, 7, and 8 for the IGMP suppression and the join and leave sync. And also for the OASM or the layer 3 multicast, it'll be route type 10 and also the SMET route type 6 route. So those will be the routes that we'll be diving into in this later session. Next slide. Okay, I'm nearly there. Before I hand back to Mitch, I just wanted to provide a sort of high-level diagram of the asymmetric forwarding behavior. Just hopefully everyone is aware of it. We are assuming, by the way, a level of familiarity or understanding with EVP and VxLAN, because we are going into these topics pretty quickly into some depth. But from a distributed gateway forwarding paradigm, the asymmetric IRB, why is it called asymmetric? Well, looking at the diagram, it's only got a routing lookup on one side. The reason being is that, the best route for this is configured locally. So you will route into a destination subnet, in this case, VLAN, there's 30/30/30 subnet or VLAN 30, and then you will bridge over. That's asymmetric forwarding. Next slide shows the symmetric forwarding. And here we have configured a shared layer 3 VNI or shared domain between all the VTEPs for routing into subnet. So in this scenario, it's very much a traditional routing model. Routing is symmetric, so we will be going into the shared IPVRF for reachability to that remote subnet. And then the destination VTAP will actually route out of that, for want of a better word, and then bridge into the destination VLAN. So looking at that diagram, it's symmetric. We term this really the routing model. So whether you're routing to a non-local remote subnet or you're routing, via into subnet to a host and following a host route, you're going via the shared IPVRF. And Mitch will go into the details in all of these routing use cases and how we achieve this and the different configuration options between these routing models. And with that, I think I will round up and hand over to Mitch. We will interject, I'm sure, with any questions and clarification points as we go through. As I mentioned, it's a pretty open form. We're trying to get through a fair amount of content within an hour or so we'll be moving along, but please ask questions and we'll answer live. That, Mitch, over to you.
All right, cool. Cool. Well, thanks, Russ, for setting the stage. At this point, we're going to kick over to a live environment where, kind of over the course of 4 scenarios, we'll see the configuration and as it relates to the origination of the type 2, 3, and 5 routes in particular. But rather than just the configuration, we're going to spend time investigating the components of each route type and ultimately how they relate to the data plane forwarding operations, which will then validate the data plane using some packet captures. But before we actually just jump right into the CLI, we'll take a minute and actually review the topology that we're going to be using throughout all of our scenarios today. As Russ called out, it is layer 3 leaf and spine. And we, as he also called out, we have options here. In this particular topology, we can see that it's BGP, more specifically external BGP, used to provide IP reachability within the underlay. And it's also used to establish the peerings within the EVPN address family that will act as our overlay control plane. Now, the point-to-point links themselves, they're really not relevant here. They're just going to be used primarily as transit. But the loopback interfaces are of interest on the spine and leaf switches. Loopback 0 in this case is going to be used in the environment to uniquely identify that node in the topology. And it will also be used as the source interface for peerings established in the EVPN address family between the leaf and the spine switches. Loopback 1 will ultimately serve as the source and destination of our VxLAN tunnels. So you see here on leaf 1A and then 2A and 2B, they each have their own loopback 1 defined. And leaf 2A and 2B are essentially presenting themselves as a single logical VTEP by having the same loopback 1 IP address on each other. So we can just ECMP towards them. Now, in the interest of time, leaf 2A and leaf 2B already have all of the relevant VxLAN and EVPN configuration applied. Also, all nodes in the topology already have their BGP underlay and overlay peerings established. So if we actually kick over to the lab session here and take a look at the topology, just a simple show IP BGP summary, we can see that, okay, these are our peerings inside of the underlay. Those are all established. Show BGP EVPN summary. We also have our peerings in the EVPN overlay. And we see here that leaf 1A is originating a whopping 0 amount of control plane into EVPN. And this is because leaf 1A is where we're actually going to spend all of our time from a configuration standpoint today, but we'll actually use the other nodes in the topology to actually validate the control plane as we go. So without further ado, let's actually just jump right into scenario 1. And we're really going to, in this scenario, we're really going to explore the type 2 and the type 3 routes. We're going to stand up a new layer 2 VPN service. And to do so, we're going to use a VLAN-based MAC VRF in the EVPN control plane. So it's a bit of a mouthful, but ultimately, what we're looking to accomplish here, our end goal is that host A and host D have layer 2 adjacency with each other, and they also have IP reachability. So if we circle back to leaf 1A and look at the configuration as it stands right now, if we just do a show VLAN, there's really not much going on. The switch itself has no VLANs defined. It also is not a VTEP at the moment, so there's no VxLAN interface. So just out of the gate to get started, let's go ahead and define the local bridge domain for VLAN 10. So we'll go in here and just say VLAN 10, and we'll give it a name because we're good network citizens. And then we'll actually enable VTEP functionality on leaf 1A. And in order to do this, we'll just simply create the VxLAN 1 interface. And then we will first define what IP address should Leaf1A use when it's actually sourcing VxLAN packets. And also, as we'll see later on, what IP address should remote VTEPs use when sending VxLAN encapsulated packets towards Leaf1A. And in this case, as we called out earlier, we're just going to use the IP address associated with loopback 1. So far, we have the VLAN configured and we've enabled VTEP functionality, but we haven't really done anything else beyond that. We still need to map the VLAN itself to a VxLAN network identifier, aka a VNI. And we have a couple ways that we can do this here. We can actually come in here and say VxLAN, VLAN 10, VNI 10,010. And this is perfectly valid configuration. You know, if this is the way we wanted to put the configuration in, that would work, no problem. But we also have the ability, let's say as an operations team, we get together and we decide that, you know, for all of our VLANs that are defined in the environment, we're just going to add 10,000 to the VLAN ID, and that becomes that VLAN's respective VNI that it's mapped to. So we can define a just range of VLANs here. Let's say it's 10 to 1,000, and then we say they map to VNI 10,010 to 11,000. Now, one thing to call out with this pre-provisioning of the VLAN to VNI mappings is that it doesn't come with the penalty of any unnecessary control plane state, and it also doesn't come with the penalty of any unnecessary hardware consumption. Meaning, for example, just because we have VNI 10,020 defined and mapped to VLAN 20, if we look on the switch, VLAN 20 still doesn't exist. So it doesn't just create the VLANs behind the scenes because the mappings are in place. So at this point in time, we have VLAN 10 defined and it's mapped to VNI 10,010. We can validate that just by doing a show VxLAN VNI 10,010. Now, what we don't have here is a way for Leaf1A to ensure that remote VTEPs that are also servicing this layer 2 VPN, this bridge domain, get a copy of the broadcast frames, the broadcast, unknown unicast, and multicast frames, commonly referred to as BUM frames, originated locally within this bridge domain. So for example, if host A sends an ARP request, Leaf1A needs some mechanism to understand that Leaf 2A and 2B, the loopback of 2222, needs to receive a copy of that particular broadcast frame so that host D can receive the broadcast and reply. And this is done via a flood list. We could manually configure the flood list here, and we could say VxLAN flood VTEP, and then define a list of VTEPs. We could choke it down on a per VLAN basis, VLAN 10, flood, VTEP, whatever. And in this environment, in this little lab we have here, this would be perfectly valid, right? So it's a small environment, but in the real world, if we're actually deploying this at scale and potentially adding and removing leaf switches from the environment, maintaining this flood list becomes an administrative nightmare. It's just not sustainable. So this is one of the first big benefits of EVPN, and actually the purpose of the type 3 route, which we're going to explore in a second, is we can leverage BGP to dynamically maintain the flood list on all of our VTEPs within the EVPN domain. So let's actually jump into BGP here and start configuring the per VLAN MAC VRF. And so to actually stand up the MAC VRF, it's pretty straightforward. We can just go into BGP and say VLAN 10. Once it's defined, at that point in time, we've created a MAC VRF for this bridge domain. Now, a MAC VRF, it's similar to an IP VRF in that it's just going to originate reachability information, but in this case, it's going to be reachability information related to a layer 2 VPN service. So for example, MAC address reachability, or the interest in receiving BUM traffic for a particular VNI. And because it's a VRF, we still need a way, as Russ called out earlier, to really uniquely identify the control plane state originated by this particular VTEP. So Leaf1A, we can use a route distinguisher, and then from here, we can really make it whatever we want to make it at the end of the day. It's really going to become something : something. We can manually define it. We could set it as auto if we so choose. But let's say as an operations team, we get together and say, you know what, to help with troubleshooting, let's make the first portion of the route distinguisher the unique identifying loopback of the VTEP originating the reachability information. And then if it's a VLAN-based MAC VRF, let's make the second portion of it the VNI that's actually associated with the bridge domain that in that MAC VRF. So we define the route distinguisher, and then next, Russ alluded to this earlier as well, we need the route targets to perform the import and export operations in the control plane and ultimately the forwarding plane as we advertise and receive information within this MAC VRF. So for example, if we say route target question mark, we see that we can specify just simply both or import and export. The idea here is that, for example, if leaf 1A originates reachability information for host A, and it originates a MAC address into EVPN, it'll go ahead and apply the route target associated with this MAC VRF into the extended communities field of the update. And we'll see this later on when we go through the actual payload of the update, the NLRI. But the idea here is that when a remote VTEP receives the update, it can look at that route target and then import it into whichever MAC VRF and ultimately bridge domain that it has associated with the import control for that particular route target. So in this case, we'll just make it the first portion 10,010, 10,010. Now we're going to put both in here because we're going to use it for both the import and export operations. But before we actually apply this, let's actually run a couple commands here and see what state, if any, is currently being originated by leaf 1A. So if we come back here, let's just go ahead and clear this scroll back on this guy. And we're going to use a watch command, which is going to refresh the output of a show command on the screen for us at an interval that we define. We're just saying every 1 second, refresh the output of this particular command, which is saying, show me the type 3 route originated by this particular VTEP, which is leaf 1A, associated with VNI 10,010. So if we hit enter here, we really don't see anything yet. Yeah, let's actually try the type 2 route. So the type 3 is not there yet. If we look at the type 2, we'll investigate this one on spine 2. Same thing, but we're looking for a different route type. And in this case, we're looking for the MAC address of host A. So the type 2 route associated with reachability information for host A's MAC address. And we still don't have any state here either. Now to kind of show how the control plane actually populates based upon these route types, we'll hop on leaf 2A and we'll do a show VxLAN flood VTEP. In other words, we're going to watch the flood list that's associated with this particular VTEP. And then on to B, we're going to watch the VxLAN address table, which is ultimately going to program the MAC address table at the end of the day with the VxLAN learned MAC addresses. But right now we can see there's a whole lot of nothing. Let's actually go to leaf 1A and let's define the route target. Now, as soon as we define the route target, we see that we have the type 3 route originated via leaf 1A into the environment. And it's saying exactly what we covered a little bit earlier. For this particular, for the bridge domain that a remote VTEP has mapped to VNI 10,010, if any broadcast, unknown unicast, or multicast packets are received within that bridge domain that's mapped to this VNI, please perform VxLAN encapsulation and send a copy of that broadcast frame, or whatever it is, the BUM frame, towards this particular VTEP, which in this case, as we know, is leaf 1A. So leaf 1A is just advertising its interest in receiving BUM traffic associated with this particular VNI. If we look at leaf 2A, we see, okay, well, it received the type 3 route, and then after it received that, it actually populates the flood list and says, okay, well, for bridge domain 10, I need to make sure that any BUM frames I receive within this bridge domain from locally connected hosts, I need to make sure that the VTEP at 2221 receives a copy of those. So at this point in time, the broadcast can work, but we still don't have the reachability information for host A. And the way we get that in the last command here is we're going to do a redistribute learned inside of the MAC VRF. So if we do a show active, which is just a context sensitive aware command that just shows you the active configuration of whatever the current config context is, it says that for the VLAN-based MAC VRF, we have this particular route distinguisher defined to uniquely identify the routes originated by leaf 1A. For the import and export operations of control plane state, we're using this particular route target. Last but not least, we're taking MAC addresses that are learned in bridge domain 10 and originating reachability to them via EVPN type 2 routes. Let's go to host A and actually try this out. So ping 10, 10, 10, 200. Okay, so at this point, the pings are working. We've reached our goal, but let's, instead of just declaring success, let's go back and actually review what else changed. So at this point, as soon as leaf 1A learned the MAC address of host A in VLAN 10, it originated the type 2 route, the MAC IP route, for this particular MAC address. Here we can see everything that we just covered. The route distinguisher that uniquely identifies this in the EVPN domain, the route target that in this case denotes both the MAC VRF and the bridge domain that the MAC address should be imported into. And then the VNI associated, more specifically, the globally significant VNI that is associated with the locally significant bridge domain on leaf 1A. So at this point, we should expect to see that leaf 2B, and he does, has learned via EVPN, the MAC address of host A is reachable in bridge domain 10 via VxLAN and egress VTEP 2221. So from a configuration standpoint, this really kind of wraps scenario 1, but let's actually go to let's take a look at the data plane and make sure that we're seeing what we actually expect. And to do that, we're going to run a packet capture. So let's do show run section monitor session. And here we see that we're looking for anything ingress or egress interface Ethernet 1, and we're going to take any of that traffic and kick it up to the CPU. So we're going to see not just traffic to the switch, but also traffic through the switch. In other words, the data plane. In a real environment, it'd be a good practice to filter this, and we certainly can filter this. But for this lab demo, it's just easy to say send it all to the CPU. Okay, so it's defined, but let's actually go over here and kick off the packet capture. Rather than doing it on the switch itself, what we're going to do is actually leverage an SSH session to the switch, send the TCP dump command that we want to run on the switch, and then the output of that TCP dump session will be sent back to our local workstation via the SSH session we have established to that switch and be piped out to our local Wireshark application. Kind of show this in action, let's actually run the command. Wireshark is launched, and from here, we need to actually say password admin. And then if the packets are following the path through EOS1, what we'll see here, we're not seeing the pings because what's happening is the pings are actually going through spine 2. So let's actually go on leaf 1A and E2, and let's shut it down. Let's go back to our packet capture, and now we see the pings. So we kind of show some convergence there as well. But now if we look at the data plane, let's validate the control plane that we just walked. So we know it's a ping, ICMP. In the inner IP header, we have the source of host A and the destination of host D. This is expected. In the inner Ethernet header, we can see that under the covers, these are just Raspberry Pis. So source of host A's MAC address, destination of host D's MAC address, just standard bridging. Now in the VxLAN header, we should expect that this is going to have a VNI of 10,010 defined, because that's the globally significant VNI mapped to the locally significant VLAN or bridge domain on the switches. And that's exactly what we see. Port 4789 UDP, that's the standards port for VxLAN. And then in the outer IP header, we see, as expected, the source address of leaf 1A's loopback 1, and then the VTEP 2222, which is the egress VTEP that was advertising reachability for host D's MAC address. Now the outer Ethernet header, this is just going to follow just traditional routing and bridging semantics, where on a hop by hop basis, as the packet is routed towards the egress VTEP, this will be rewritten as needed. So this really wraps scenario 1. Before just jumping right into scenario 2, we'll go ahead and pause for questions. So Russ, Alex, any questions outstanding right now that we should address?
I don't think there's any questions. Maybe a few around the topology, and maybe we can just have a look at the BGP configuration, because I think it's important just to show, like, really once the BGP VPN configuration, the core underlay and overlay was set, the only thing we really added was a VxLAN to VNI mapping and a VLAN and a MAC VRF. So maybe just have a look at the BGP configuration just for folk on the phone here.
Sure. Yeah, let's go ahead and
the rest.
Okay.
And we will provide these. There's been a couple of questions on where are these configurations and so on and so forth. I did just put a link in an answered question to the deployment guide. All of this is covered in the deployment guide. In fact, if you read that, you'll see this is very familiar. So there's a deployment guide to review the configurations and best practices as well. So I don't mean to break your...
No, it's worth being able to see the BGP configuration. So let's actually jump in and see what's going on to actually build the control plane that's hosting these different route types that we're sending around here. So on the spines, you can see the configuration. It's pretty benign. There's not a whole lot here. There are options, just like we have options for the underlay of the layer 3 leaf spine. we have options for how we actually want to define our peerings inside of BGP. We could statically define them, or we could use a listen range and then enable some dynamic peering. So as a leaf sends a TCP SYN to port 179 and eventually a BGP open message, we can say if it comes from this particular address range and it's coming from the proper range of BGP ASNs that we're expecting, and it's authenticated, so there's some security around this, go ahead and accept and establish the session. So to keep the spine configs pretty lean, we're actually leveraging dynamic peering in this environment. Now with BGP dynamic peering, at least one side of the peering needs to send the initial TCP SYN and eventually the open message. So on the leaves, we have, very similar, we have the underlay defined using a peer group. And then we have the overlay defined as well using a peer group. Important commands here really would be, so we want to make sure that the EVPN control plane, that peering is using loopback 0, as we discussed earlier, to establish those peering sessions. Also, send community is very important, and by default, we'll send both standard and extended communities in EOS. But this is important because as we're going to see as we look through the NLRI, or the payload of the BGP routes associated with EVPN, we're going to see that it makes extensive use of the extended communities fields.
Yeah. All right. So I'll just answer a couple of these questions that are all flowing in now from anonymous attendee. Yeah, the type 2 routes, but just keep in mind we're at scenario 1, so we need to keep it going here. We're only doing MAC routes, right? There are no SDIs associated with this VLAN that Mitch just configured. This is a VLAN-based service, so there's just MAC routes that are floating around. So in a further session, we will see, or not session, scenario today, we will see the MAC IP or the ARP routes as well. We're neglecting to include redistribute learned in the MAC result in flooding. Yes, it will. If you don't redistribute learn, you'll just be flooding to the bum replication list, right? So configure, obviously, redistribute learned. Or if you want to do static, you can do redistribute static. I think I answered some of them here. You need to disable EVPN peer group. Ideally, from the IPv4 underlay, yeah, you could disable it to make sure that you're not sending to both. So that's in the deployment guide. If you go through the deployment guide, it'll have all of our configuration options.
Was that question referring to just disabling IPv4 unicast peering by default?
I think so, yeah.
Okay, cool.
Fine.
Yep.
Yeah, by default.
Yeah,
it's done by default, and I think in this one, so that's one of the options. You can either disable it explicitly or by default, right?
Yep.
Okay. With that, I think we need to move on to scenario 2.
Yes, we'll move at a relatively brisk pace, but we'll keep it going here. Please keep the questions going. We definitely want this to be interactive. Okay, so as Russ had called out, so far it's just the MAC IP routes, so the type 2s and the type 3 routes. And it's exclusively been bridging scenarios thus far in our first one. In the second scenario, it's going to be exactly the same. We're going to stand up a new layer 2 VPN service, except in this case, we're going to leverage a VLAN aware bundle, which will allow us to map multiple bridge domains into a single MAC VRF. Whereas in the first scenario, we had a one-to-one mapping MAC VRF to bridge domain in a VLAN-based configuration. Regardless of the approach, though, the end goal is still the same. We want host B, in this case, to be layer 2 adjacent to host E in the bridge domain, the VLAN 20, and ultimately be able to ping each other, have IP reachability. It's just the way we get there with the configuration will be slightly different. So if we go back to 1A and kind of explore what's going to be different here, let's go ahead and review under our VxLAN interface. We have the VLAN to VNI mappings predefined. Of course, we know that VLAN 20, just because they're mapped, that doesn't mean VLAN 20 is just dynamically created behind the scenes. So far, there's really been no penalty from a control plane state or a hardware resource consumption state from doing this provisioning. Let's actually go into BGP now, and instead of configuring and just saying VLAN 20, which would be a VLAN-based MAC VRF, let's go in and say VLAN aware bundle, and then from here, we'll just call it tenant-A. So right out of the gate, we see that, yes, okay, it's still just a MAC VRF, but the primary difference is going to be this next command. We're going to specify that VLANs 20 and let's say through 39 are all mapped to this local MAC VRF. These bridge domains are all mapped here. Now, it is a VRF, so we still want the ability to be able to uniquely identify the control plane state originated by this particular VTEP, And just like we did in the first scenario, we'll just make it something that means something to the team operating the environment. So in this case, let's say we agreed upon the unique identifying loopback of the originating VTEP, and then a colon, and then maybe in this case, because we have multiple bridge domains mapped to a single MAC VRF, instead of using one VNI, we could say tenant A's ID is 1. So we'll say :1. And then the same rules apply for the route targets, where this is the import and export operations for the control plane state as its exchange between the VTEPs. And instead of saying the same VNI twice, what we can do here is, again, we just make this something that means something to the team operating the environment. Maybe the first portion is the first VLAN in the bundle, and the last portion is the last VLAN in the bundle, the VNI that's associated with that VLAN. And we need to make sure that we put both here because, again, it is import and export operations. So if we don't, it'll actually bark at us like it just did. And same as in the last example, redistribute learned. And at this point, the configuration is complete. So show active, and we see that we have our VLAN aware bundle, and we also have our VxLAN interface. So here we've predefined a mapping of bridge domains to a MAC VRF. And again, we have the VLANs already mapped to their respective VNIs. Now, if we actually go to the spines and we look at some of the control plane state again, let's go back to spine 1, but this time, let's actually look for a type 3 route associated with VNI 10,020 that's coming from a leaf 1A. And now we don't see anything. Same thing again on spine 2. Let's go ahead and look for the MAC address associated with host B. We'll look for the type 2 route that was originated with this MAC address. And we don't see anything yet. We also see that on leaf 2A and leaf 2B, they still just have, their flood list just says for bridge domain 10, any bum frames we receive from locally connected hosts, create a copy of those and send them to this egress VTEP so that it can also send those broadcast or whatever those frames are to its locally connected hosts. But we don't see 20 here yet. So at this point in time, our configuration's done. We could actually just say, all right, that's a wrap, and walk away. And there's really been no penalty from a control plane state generation or hardware resource consumption. VLAN 20 still doesn't exist behind the scenes. Let's say like a week from now, someone from tenant A comes up to us and says, hey, I'm connecting some devices to, host B is on 11 on leaf 1A, and then E is connected to 11 on leaf 2A. What we can do is say, all right, well, let me go ahead and configure Ethernet 11, and it's just a simple access port. It could be a trunk, whatever it is. It just has VLAN 20 connected here. And then after that, let's actually start the pings. Right now, host B cannot ping host D. If we go to leaf 1A at this point and we just say, okay, are you ready for the service to be turned up? And we create VLAN 20, at that point, reachability occurs. The reason being is that as soon as we create the VLAN, then the type 3 route is originated. And the type 2 route is originated for that particular MAC address. If we look at leaves 2A and 2B, now VLAN bridge domain 20 is actually a part of the flood list on these VTEPs, and they know that if they receive a bum frame within bridge domain VLAN 20, they should send a copy of it to this VTEP because they know that this VTEP is interested in that traffic because they learned via a type 3 IMET route. And then leaf 2B, it actually said, okay, well, I learned via EVPN type 2, the MAC address of host B in bridge domain 20 is reachable via VxLAN VTEP 2221. So we kind of see the configuration differences there, but ultimately we accomplish the same task. We just approached it a bit differently. So the advantage, if we revisit here on leaf 1A, if we revisit show run section router BGP in this case, the VLAN aware bundle, we're just mapping multiple bridge domains to a single MAC VRF. Now, let's actually take a second and look at this type 2 route that was originated in a little bit more detail. So kind of try to figure out, okay, is there anything different whether we use a VLAN based or a VLAN aware bundle method? So from the perspective of leaf 2A, what does it see? When it sees this type 2 route, it sees, of course, the MAC address. It knows it's a type 2 route, MAC IP. It has the route target in the extended communities field. And in this case, the route target can only signal the MAC VRF. Remember, we have multiple bridge domains mapped to the single MAC VRF. So just using the route target alone isn't enough to actually ensure that we import this MAC address into the forwarding plane for the proper bridge domain, AKA, in other words, what MAC address table do I put this thing into? So from here, what we'll do is we'll actually make use of this value here. This is referred to as the Ethernet tag ID. This was done automatically. You saw we didn't have to do anything to actually make this happen, to actually make this part of the route. But in a VLAN-based model, we'll see that it would be here. It doesn't exist because it's a one-to-one mapping, bridge domain to MAC VRF. We can use the route target for the import operations entirely. But with a VLAN-aware bundle model, we have multiple bridge domains mapped to a single MAC VRF. We need some way to understand what MAC address table do we actually import this MAC address into. So if we need to actually manually set this, we do have a knob that we can use to say, you know what, we don't want to use just dynamically whatever VNI is mapped to that local bridge domain. We can actually statically set this if we so choose. But by default, the Ethernet tag ID will be set on a VLAN-aware bundle originated route to whatever VNI was associated with the bridge domain locally on that particular VTAP. Now the data plane operations are exactly the same as they were in scenario 1, so we won't have to go through the packet capture again. But before just jumping into scenario 3, I do want to pause for any questions. So Russ, Alex, anything else jump up that we should address?
Not. So go ahead, Alex, if you.
No, yeah, there was a quick one, Mitch. There's a question regarding, well, probably a bigger question as well. Are you running this on, is this on a VOS image, or are you actually running this as on hardware?
Good question. So in this environment, we're actually running on hardware, but everything that we see today runs just fine in virtual EOS. So if you wanted to go grab an instance of VxLAN, spin it up and create this topology, it'll work just fine.
Thanks, Russ.
And we, yeah, sure. We have a couple of other questions around, MAC routes. We call them MAC IP routes in our CLI. So I think once we move into this session, you have currently only seen the MAC route being advertised. That is correct. You will soon see the MAC IP route with dual VNI tags. We just show them under the one stanza. You can search on MAC, and in next release, you'll be able to search the database on IP. So just, it's, I guess, just verbiage. And I'm trying to think, I think the other one was showing the ARP and showing the MAC. And so far, Mitch has only been working on MAC VRF, layer 2 only, so just MAC addresses. So the command he's using will just show MACs. I believe we'll get into the next section where you'll see the ARP entries, so on and so forth. I do just want to mention one thing on that route type as a call out to our next session, or in a few sessions time. The ESI value is 0 because we're not using active ESI multi-homing. It's a question we often get, and obviously MLAG does not use ESI multi-homing, so that's why that ESI value is 0 in that route as well.
All right, good to keep going?
I think so. Yes, we do.
All right, so everyone's favorite topic, IRB models. Let's go ahead and jump into, we'll cover the asymmetric and the symmetric models that Russ touched on earlier. We'll configure them up and we'll actually validate the control plane and the data plane as it relates to each respective model. But to start out, we'll focus on asymmetric, and ultimately the goal here is host A can ping host C. We see here that we're now moving beyond just bridging to we have two hosts in different subnets within the same tenant VRF, in this case, VRF A. But we'll see that it's still VxLAN bridging operations between the VTAPs themselves. So rather than spend too much time in the diagram here, let's actually configure this up and then actually walk the control plane and then check the packet captures and see what happens once the configuration is complete. So let's go ahead and go in here and hop into Leaf 1A. And we will actually define a SVI for VLAN 10, because as it stands right now, we have a whole lot of nothing in here. So anything that Leaf 1A gets from a layer 3 forwarding standpoint for routing in VRFA, it's a goner. It's going to get sent to the bit bucket. So let's go ahead and change that. Let's create an interface for VLAN 10. So we have our SVI. It's a member of tenant A, so VRFA. And then we'll define the IP address, and we'll say virtual 10.10.10.1/24. The IP address virtual, this is a method to maintain a consistent gateway IP and MAC address across all of the top of rack switches inside of the EVPN domain. So every top of rack switch will have every top of rack switch that's a VTAP operating as the first hop router for their local bridge domains will actually have this particular address for, in this case, VLAN 10, the SVI. For the MAC address, if we actually do like a show run grep and look for virtual router MAC, what we'll see is that in the global configuration context, we've just set the virtual router MAC address. For simplicity's sake, it's just set to ABC. This could be any valid MAC address that we want it to be. But the idea here is that it's configured in the global configuration context, so we have a consistent MAC across all of our SVIs as well. So at this point, we have the actual SVI defined. We have the MAC address. Let's make sure it's actually up and operational. And we see that, yep, it's up. And let's go to host A, and let's stop pinging and just bridging to a remote host. And let's go ahead and make sure that it clears an ARP table, and then it says ping 30303100, and right now it's still not reachable. Now we know a second ago we looked at leaf1a, we can kind of guess as to why this is happening. Show IP route VRFA, we see that, okay, well it doesn't have a route to the 30 network. So leaf1a just says, all right, well thanks, but I'm just going to discard this packet. I don't know what to do with it. So in order to ensure we have the reachability, what we need to do is actually stand up the bridge domain for VLAN 30. Now everything behind the scenes from a EVPN standpoint, saying that like the type 3 routes, for example, as soon as we created the VLAN, we had that all pre-provisioned. The control plane's already being built out. So we have the VLAN, now we can create the SVI for VLAN 30. And same thing, we can say it's part of VRFA and IP address 303031/24. Now at this point, with the SVI defined and configured, we see that the pings actually start working. So to really understand the differences between the asymmetric and the symmetric models, let's actually just jump on the whiteboard real quick, and then we'll take a look at this in the data plane, just via a packet capture. All right, so what happened here in an asymmetric model is that host A sends the ping, and it reaches the first hop router, which in this case is the SVI on leaf1a. Leaf1a, as we saw, needed to make a local routing decision to route into the destination subnet. So it makes a local routing decision into the SVI, into the network 30. Once it's actually in that particular subnet, now it can make a bridging decision to send the ping ultimately to host C. Now it's going to say, okay, inside of this particular bridge domain, VLAN 30, where does host C actually reside? And we know via a type 2 route that the MAC address for host C exists behind the VTEP located at 2222. So we perform VxLAN bridging towards the egress VTEP, and we use VNI 10,030 on the way over. And then on the way back, it's the same thing, just in reverse. Host C replies, it goes to the first hop router, a local routing decision is made into the destination subnet, and then from there, VxLAN bridging is used in the opposite direction, back towards host A, and then once leaf1a receives it, it looks at the VNI, and says, okay, well, I have that VNI mapped to this bridge domain, and then it makes the appropriate lookup and forwarding decision in VLAN 10, and then host A gets the reply. So a little bit going on there. We see that with asymmetric, though, one of the big reasons it's referred to as asymmetric is that on the way there, we used VNI 10,030. On the way back, we used VNI 10,010. It was bridging in both directions, but it was a different VNI. And also, even though we have no hosts locally present in the bridge domain associated with VLAN 30, we still needed to actually have the VLAN created and the SVI locally defined so that we could actually route into that destination subnet. So we'll take a look at this on the wire via packet capture. And then after that, we'll pause for questions and then move to the symmetric mode of operations for IRB. So to make sure that we actually see the packets as expected, let's go in and say again, leaf1a in E2, see you later. So spine 2 is out of the game for anyone that wants to talk to leaf1a. Let's go make sure the pings are still rolling, and they are. And then we'll go over to our capture. We'll actually stop this one. That's old news. See you later. And let's go ahead and launch Wireshark again. It's going to ask for our password. And at this point, we should see there are the pings. So let's go ahead and stop this and say, you know what, BFD, you're not really interesting to us right now. So see you later. But we are interested in this. So in this case, we have the source and destination IP addresses of host A and host C in the inner IP header. This is expected. The inner Ethernet header looks a bit different than what it did before, though. In the inner Ethernet header, we see the destination MAC address is still host C, because ultimately leaf 1A is performing VxLAN bridging towards that host. And we see that it's actually sending the VxLAN packet to the proper VTEP at 2222. But because it made a local routing decision, the Ethernet header is rewritten on a hop-by-hop basis. That was technically a hop. So the source MAC address in this case was actually the MAC address associated with VTEP leaf 1A. Now the VxLAN header on the way there, we're using VNI 10,030 because we're bridging towards host C. And again, the outer IP header is, as it's been the entire time, the source and destination IP address in the header is always going to be the loopback1 address or whatever address we've assigned to the loopbacks of the VTEPs in the data plane. And the outer Ethernet header, again, this just changes on a hop-by-hop basis as the VxLAN packet is routed towards the egress VTEP. On the way back, the big difference on the way back is that we're using VNI 10,010. So just, again, show the comparison here, 10,030 on the way there, 10,010 on the way back. So that's primarily why it's referred to as asymmetric. It is still VxLAN bridging at the end of the day. We're still making a local routing decision. We'll see with the symmetric mode of IRB, it's a bit different in that it's going to be more of a pure routing model. But before we just jump into the CLI and start configuring that, let's go ahead and close out Wireshark and we'll pause for some questions. So Russ, Alex, anything out there for questions?
Yeah, I mean, a few questions there really regarding the whole symmetric, asymmetric thing, which I think we're going to cover at the end in terms of the different models and where they add value to each other.
Okay.
All right, so probably leave that to the end once you've covered, and we can kind of sum that. I think you're going to summarize that up at the end.
Yep. Yeah, we'll definitely compare and contrast the two models once we're finished up with scenario 4. Okay, so good to keep going?
I think so. And from you, Russ?
No, I think we get going and just answer these questions at the end. We'll store them up.
Okay, so for the last scenario, last but certainly not least, the symmetric mode of operations for IRB for routing and bridging. And right off the bat, we'll see it's a bit different. The end goal is still the same, right? We just want IP reachability between host A and host C within the tenant A VRF. But in this case, the way we're accomplishing that is just a bit different. And that we'll see that it's actually performing VxLAN routing using the layer 3 VNI 50,001 as opposed to VxLAN bridging using the L2 VNIs in each respective direction. So to really call out like how this is actually different from a configuration and a control plane standpoint, let's just jump right back into the configuration of 1A. We'll start to build this out, and then we'll see how the control plane changes based upon defining things such as the layer 3 VNI. And I think someone alluded to this earlier, the MAC IP route. In this case, we're going to see the IP portion of it. This is where we're actually going to start to see the L3 VNI. It's a bit of a spoiler there. On 1A, right now, we know that we had to have the SVI for VLAN 30 and VLAN 30 actually locally defined as a bridge domain in order for the reachability from host A to host C. Let's go ahead and get rid of that. Let's say, you know what, for no int VLAN 30, see you later, and also no VLAN 30, see you later. At this point in time, the pings have stopped. So poor host A can no longer ping host C. We're going to fix that. But instead of using the asymmetric model this time, we're going to use the symmetric model. And one of the first steps when we're going through the symmetric model is that we need to actually map in the VxLAN interface. We need to perform a mapping here. And that mapping is going to be between a VRF and a VNI. So up until this point, our mapping to VNIs has been exclusively just layer 2 centric bridge domain. It's been bridge domain maps to this respective VNI, so VLAN 10 to 10,010. In this case, we're actually taking an entire VRF and mapping it to a single VNI, which when we do this, we actually refer to this as the layer 3 VNI. A way to think about the layer 3 VNI is that anyone familiar with MPLS VPN v4, you could think of this as the VPN label in this case, where it's going to signal the VRF that should be used for the lookup and forwarding operations once a VTEP performs decap and inspects the inner IP header of a packet. So in this case, we'll go ahead and define the VRF to VNI mapping. And then after we define this mapping, next we need to make sure that we actually have this VRF locally defined for this tenant inside of BGP. So again, up until this point, it's been all MAC VRF, but let's go ahead and let IP VRF have some fun here. And let's actually say VRF-A. And route distinguisher, again, we want this to just be maintained as a, we want the ability to uniquely identify the control plane state originated by this VTEP. And let's just say it's loopback0, the ID of the tenant. So RD11111:1. Just like with the MAC VRFs, we still need to actually define the route targets. And in this case, we're going to import the EVPN route targets 1:1 and then export the same value. And this is what we'll see in the extended communities field of the type 2 MAC IP route. And then we'll also redistribute connected prefixes inside of this VRF into the EVPN control plane. So reachability to, for example, 10.10.10.0/24 will be originated via leaf 1A. And it'll do that using a type 5 route, which we'll investigate last. But at this point, we actually have, let's review our configuration. And we see that we have the VRF mapped to a layer 3 VNI. And in BGP, we see that we actually have the tenant VRF defined as well. So at this point, if we look back here, the pings have started to work again. But before we just jump into the packet capture, which we're going to do in a second, let's revisit the control plane state that was originated, the type 2 route that was originated for this host. So if we go back to leaf 1A, showing it VLAN 10, okay? And if we come back and actually look for the MAC IP route associated with host A, what we should see, and let's go ahead and clear off some of the noise here. What we should see is that we now have there's a bit more going on. This is the route we've seen so far. Someone I think alluded to this earlier, it's just the MAC route, and that'd be accurate. It is just the MAC address. But now down here we see MAC, it's the MAC IP. We actually have the IP now. So we have the IP of the host, the IP plus the MAC address. We can use this to populate our ARP tables or understand the ARP entries related to this particular MAC address. What IP is it? We also know that the layer 3 VNI is 50,001. So when a VTEP sends a VxLAN encapsulated packet towards leaf 1A and it's destined to 10.10.10.100, they can apply VNI 50,001 in the header. And when leaf 1A sees this, it's going to say, well, I know when I perform decap that I need to perform the lookup and forwarding operation in VRF-A for this particular packet. Now, the control plane is still driven by the route targets, right? So here we have the route target associated with the IP VRF for tenant A, and we still have the route target that's associated with the MAC VRF for, in this case, bridge domain VLAN 10, which we saw earlier is just a VLAN-based MAC VRF model. There's a couple other entries in here, primarily the EVPN router MAC. We're not going to go into too much detail on this today. We'll give it a little bit of a shout out, but we'll go into much more detail on this particular entry once we reach the MLAG session in a future session. So it's working. Let's actually take a look at leaf 2A or 2B. And let's see from a routing standpoint, instead of just having an entry to 10.10.10.0/24, we now have via the dual VNI type 2 route that was received, we now have a host route towards host A. And the information we have here is for reachability to this particular IP address, it's reachable via the VTEP 2221. When we send the VxLAN encapsulated packet towards VTEP 2221, we should put VNI 50,001 in the header to make sure that that VTEP performs the lookup and forwarding operation in the proper VRF. Last but not least, because we're not really bridging to that VTEP, we're going to be routing between the VTEPs. We need to make sure that when the destination VTEP of 2221 receives the actual VxLAN packet and performs decap, it needs to make a routing decision to route the actual packet into the destination subnet after it does the VxLAN decap. So in other words, it needs to take action on that packet, on that frame. So the destination MAC address in the inner Ethernet header, we'll see that it's actually going to be the router MAC that's associated with VTAP 2221. So that was a mouthful. Let's actually take a look at it in the data plane and have it make a little bit more sense here. So again, let's make sure that we are going to force the traffic to go via spine 1. Let's make sure we still have our interface shut down. And it's still down. Cool. Over here, kick off our packet capture. And then there we go. And there's the pings. Let's go ahead and stop. And again, see you later, BFD. You are of no interest to us. All right. So looking at this on the wire, it's still a ping. And it's still a source and destination. The inner IP header is host A and host C. The inner Ethernet header, this is entirely different though. So we've seen it where the source was the router MAC of the VTAP that originated the VxLAN packet, but the destination previously was the MAC address of the actual endpoint itself. In this case, the source MAC address is the MAC address associated with the source VTAP, and the destination MAC address is the MAC address associated with the egress VTAP. In other words, when the egress VTAP strips off the VxLAN header after seeing that it's 50,001, it knows it has to take action on this particular frame because it's destined to it itself. Once it does that, it looks at the IP header, makes the routing decision into the destination subnet, and then ultimately forwards the packet to that host. But we'll see in both directions, the source and destination MAC addresses in the inner Ethernet header are the router MACs associated with the VTAPs. And we also see in both directions, the VNI is the same. So again, the term symmetric, we're performing a VxLAN routing operation in both directions between the VTAPs, and the VNI is the same in both cases. So it's no longer 10,010 and 10,030 as it was in scenario 3. Now it's always 50,001. And the idea here is that we're not performing bridging, we're actually following the host route and routing towards the egress VTAP where the host resides. And then everything else is the usual suspects, everything we've seen up to this point. Destination port 4789, the source and destination of the outer IP header are the VTAPs themselves. And then again, the Ethernet header just changes on a hop by hop basis as the packet is routed towards the egress VTAP. So I know we moved at a relatively brisk pace in the interest of time. That actually concludes the last scenario for today. But before we actually go through and just do some final comparison between the different models of IRB, let's go ahead and pause for some more questions. So Alex, Russ, anything out there for questions?
I think one thing we need to show actually just is the, now we actually do have type 5 prefix routes, right? Now that we have the layer 3 VNI configured in the VRF, that was some of the questions. And asymmetric,
yes.
You know, the SVIs are in the default table, right? So arguably there could be no routing protocol. It was one of the questions. You can run a routing protocol in the default. However, now we have the layer 3 VNI. So go ahead, I should mention that.
No, that's a good call out. That's actually something I had like, hey, we should talk about type 5, and I totally skipped over it. So thank you. But yes, when we did redistribute connected, let's review show run section router BGP. If we go down here and see, we did redistribute connected in this VRF, and the reason we really did this was because we wanted to show the origination of a type 5 route into EVPN. So the type 5 route, it's should look pretty familiar. It's really just an IP prefix. It's exactly what it's called. It's for 10.10.10.0.24. It's reachable via, in this case, it's locally originated, but it can be reachable via the egress VTAPs 2222. This is the layer 3 VNI we should use if we need to perform a routing operation towards that VTAP. That way it does the lookup and forwarding operation in the proper VRF. But in this case, you know, we could, with the type 5 routes, this is where we can start to get into the layer 3 VPN services in EVPN, where the VNI operates more as a VPN label. Anything else you guys want to add, Russ or Alex? I didn't want to gloss over anything there.
I think maybe just do a show IP ARP VRF for this and doing ARP suppression. I mean, yes, ARP suppression is per VNI, of course. You know, we now take those ARP entries and program them as permanent. I don't know if we're probably going to have too much in here at the moment.
Yeah, there's not much in here in the moment. And for the ARP entries, for those interested in seeing more about ARP, please tune in for the next session because it is going to be an ARP-a-thon.
That's true. That's true.
One other thing, Mitch, as well, was, I mean, obviously this is all V4, but the question is V6 there, support as well.
Yes, there is. So if we wanted to actually originate reachability information to IPv6 prefixes in the overlay via type 5, that's certainly supported as well. So good question, good call out.
Okay, so we can, I guess we can go on to the comparison, because I think that's actually where most of the questions are kind of one versus the other. Is that the next slide? In the interest of time.
It sure is.
Okay. And I guess anyone can throw in comment here. Obviously, that draft needs to be updated to 08. So the question around, asymmetric versus symmetric, and we'll be covering this in the ARP suppression topics, and also in all of the sessions will go into a lot more detail. We honestly don't see, we support both models, of course, and you can actually even turn off a dual tag type 2 route, so you can have an ARP route or a MAC IP route with a single label and not have host routes. So there's a multitude of options in EOS. We see customers running asymmetric probably for the main reason is just simplicity. You are just using EVPN for layer 2 bridging. If your VLAN scale or SVI scale isn't too big, or you don't need layer 3 multi-tenancy, then you would simply, just have your SVIs in the default table, and you'd be stretching layer 2 wherever you wanted to. So that's one big, reason why folk would run asymmetric. The other, from a symmetric model, as soon as you need layer 3 multi-tenancy, you're in a symmetric model, really. You're running an L3 VNI. You have a shared VRF. Now, as I mentioned, you could still turn off host routes on our platforms per VLAN or per MAC VRF. So there's a lot of options in doing that. You can even, get host routes in another way. It's probably for a separate session. So symmetric, I think in general, folk have layer 3 multi-tenancy, so people end up running symmetric. That's another topic for the ARP optimization case, because we do have different models. So depending on the model, the ARP suppression or where we store ARP entries does change. So in some respects, hardware resource comes into the equation. If you're running at massive scale and you don't need everything stretched everywhere, then symmetric arguably can scale higher, because the LPM tables in the platforms are larger than the MAC tables and the ARP tables. So that's probably, one other reason. And I don't know if anyone else has anything to add, but flexibility and choice, we pretty much have whatever option you want, and they are covered in the deployment guide to some extent, especially the symmetric model. So hopefully I've covered the reasons. Alex or Mitch, anything to add?
I think it seems to be general questions there. Which one's better over the other, right? There isn't one better than the other. It's just a case of your preference and what your design is going to be, how much scale you need, where you like the idea of having the same config across each leaf, right, which asymmetric provides to you. So there isn't one better than the other. It's just a case of choice based on your particular deployment. Yeah.
And I have nothing to add. That was both of you have kind of hit on everything.
With regards to your layer 3 routing out of the domain, we'll be covering that in the DCI, stitching together EVPN domains, of course. The most common model these days is like a BGP pairing within the VRF out to external, the rest of the world. Of course, there will be options upcoming where you'll be able to do an integrated layer 3 gateway solution and advertise out directly into the rest of the world, or essentially re-originating routes. So option B. Currently, just looking at that last question, connecting L3 interfaces to border routers, most common method we see is just like an option A, BGP pairing within a VRF. Gosh, we've answered a lot of questions. Anyway, I think at this point, we could probably have pretty much stayed on an hour. Want to say thank you and actually do another call out to these ARP, the next sessions. ARP and EVPN VxLAN is for December 5th. If you think they're too far apart, well, too bad. I don't know how quickly we can get them going, but we have 5 or 6 planned out. If you have other thoughts on what you want to see, then we can add them in as well. But I think these are the critical topics we want to cover. Next one, December 5th, and we'll come up for a date cadence around a month for the next one after that. And with that, thank you. I'll pass it back to Whitney.
Thanks, guys. That's all the time we have. Just to reiterate, the next webinar of the series will be on December 5th at the same time, 10 a.m. Pacific time, 1 p.m. Eastern. If you did not get your questions answered today, please feel free to email us at webinars@arista.com. A recording of this webinar will be available on our website.